Hello, my name is Steve Miller. I'm a math professor at Williams College, and I'm excited to be a mentor again for the PolymathJrREU program. So I'm going to talk about one of my projects that on Benford's law. And so I want to discuss a little bit what are the kinds of questions we can ask, what kind of tools and techniques do we need. And if you want more details, this is an abbreviated version of a talk I gave a few months ago at UConn. If you go to my webpage, you can get links to the video of this and other talks, as well as survey articles and articles I've written with students and colleagues over the years. And again, lots of different books have now been written on the subject. So let's talk a little bit about the motivating question. So imagine you have a nice set of data. Maybe it's the Fibonacci numbers, because we're mathematicians, stock prices, etc. And you want to ask what fraction of the time is the first digit of a 1? Well, all things being equal, you might guess maybe 10% of the time. But then you quickly realize, oh, wait. If we're talking about the first digit can't be 0 unless the number is exactly 0. So maybe it should be 1 out of 9 times, because maybe the numbers 1 through 9 are all equally likely. Amazingly, it turns out that the answer is very far from that, is that the first digit being 1 happens around 30% of the time, while only around 4.6% of the time you start with 9. So this is now known as Benford's law, or Benford's law of digit bias. I'm describing what goes on for the first digit here, but you can, of course, talk about other digits as well. And so it happens with lots of different data sets. So the Fibonacci numbers is almost perfect how beautiful it fits. Twitter users, most common iPhone passcodes. We're not going to talk about how that data was obtained, distances from stars from the Earth. And you might notice that some sets seem more Benford than others. And a general phenomenon is the more sets you amalgamate, the more the amalgamation is, the closer the amalgamation is to Benford. And I'm going to discuss a little bit about the theory behind Benford's law and some examples and applications, maybe a little bit of the sketching of the proofs, but I'll probably leave those to the videos online, and then talk a little bit about some problems I want to look at with you over the summer if you choose to work in the Benford group. All right, now before we begin, Benford's law is often used to detect fraud, and it's important to realize that when you're looking at tests, just because something indicates that fraud is happening, it doesn't mean that fraud has actually happened, that there could be alternative reasons. And one of my favorite examples of this is a beautiful strip from Dilbert, where the evil director from HR rejects all of Dilbert's expenses because his meal costs are round numbers and declares that you are a liar or worse. Dilbert then exclaims, I decide what to order based on what would total a round number after 15% tip, at which point he's told that's worse. So again, when we use Benford's law to detect fraud, we're not really detecting fraud, we're detecting possibilities of fraud, and it's important to keep that distinction in mind. So here's a list of many different situations where Benford behavior with this digit bias occurs. 3 really important applications is analyzing round-off errors in computers, determining optimal ways to store numbers, and detecting text and image fraud. So let's talk a little bit about the general theory. So for many data sets, the probability of observing a first digit of d base b is the log base b of d plus 1 over d. So base 10, that means about 30% of the numbers are 1. Now, to just quickly check to see that this really is a probability distribution, if we sum this from d goes from 1 to 9, well, the log of a product is the sum of the logs. So if we have the sum of the logs, that becomes the log of the product. And you'll notice a nice telescoping sum here, and you'll end up getting just the log base b of b. So I encourage you to do that quick little exercise. So what background material do we need? Well, we need some clock arithmetic. So we say a equals b mod c if a minus b is an integer times c. So 17 is the same as 5 mod 12, 4.5 is a half mod 1. This is why if it's 10 o'clock now, what time is it in 5 hours? 10 plus 5 is 15, but on a clock that would be the same as 3. Then we can write any number in scientific notation. So we can write x as the significand times 10 to a power, where that power k is an integer. And what really matters for us, if we're trying to decide what is the first digit, is just the significant part. All k does is shift by padding zeros to the left or the right. So if we had 2020.1701, that would be the same as 2.02011701 times 10 cubed. And so now we're writing our number as x as something between 1 and 10, and some powers of 10, an integer number powers of 10. So 2 numbers will have the same leading digits if and only if they have the same significand. And if we take the log of both base 10, we see that they will differ by an integer. So the key observation is that 2 numbers have the same logarithms mod 1 if and only if they have the same leading digits. And this is a hint as to why Fourier analysis is such a powerful tool to study this. So what is Fourier analysis? This is studying exponentials. E to the 2 pi I x is cosine x plus cosine 2 pi x plus I sine 2 pi x. So here, if I give you e to the 2 pi I u, every time I increase u by an integer, I've added an integer number of copies of 2 pi I just return to where I started. Usually in mathematics, when we have a function, we can't just chop off the integer part and expect that the value will be the same, but it is true when we are looking at these exponentials. And this is the basis of the sines and the cosines. This is the basis of Fourier series, which is a generalization of Taylor series. So e to the 2 pi iu is e to the 2 pi iu mod 1. And so it's enough to understand what's going on in mod 1, so we don't actually have to chop things off. We could actually look at the log of x base 10 as the input. So other concepts we need is that of equidistribution. So we say a sequence is equidistributed mod 1, or evenly distributed, or uniformly distributed if the fraction of times it lands in the subinterval AB of 0, 1 is just the length of this interval B minus A. So in other words, if I go from 1/3 to 2/3, that's 1/3 of the interval, and I would expect 1/3 of the time I fall in there. So a big theorem in the subject that's used frequently to prove equidistribution is if you take an irrational number beta, then n times beta is equidistributed mod 1. So if you look at beta, 2 beta, 3 beta, 4 beta, 5 beta, and look at their fractional parts, it's going to fall evenly in 0, 1. Clearly, if beta is rational, this can't be true. If beta is 1/5, you would get 1/5, 2/5, 3/5, 4/5, 5/5, which is the same as 0, 6/5, same as 1/5, and you would just keep cycling. And it's a nice fact that as long as beta is irrational, then n beta is equidistributed. More interesting is trying to figure out how quickly does it become equidistributed, and that's going to depend on how irrational the number is. So a nice example proved that the log of 2 base 10 is irrational, or the log of the golden mean is irrational. And so I will skip those proofs in the interest of time. So just to give a visual example of this, let's look at the square root of pi. And so we look at the fractional parts of n root pi mod 1. And so if I look at the first 10 values, you see, yeah, it looks like it's falling pretty evenly in bins of size 1/10. It's not perfect. Well, I did this deliberately. I wanted to have the data fluctuate a little bit. But if we go up to 100 values, it's a little bit closer. 1,000 values is fairly close. 10,000 values, it's very hard to see the difference. So the equidistribution is kicking in pretty quickly. You can see slight little fluctuations. And then the natural question to ask is, how big are these fluctuations as a function of how many points we're looking at? So the fundamental equivalence in the subject is a data set is Benford if and only if its logarithms are equidistributed mod 1. And so to see this, if we write x as the significant times 10 to the k, the log of x base 10 is the log of the significant plus k. So when we look at it in mod 1, we only care about the fractional part, the k vanishes. And so if I have the numbers from 0 to 1 and 1 to 10, the log of 1 is 0, the log of 10 base 10 is 1. So which numbers have a first digit of 1? Well, it'll be all the numbers from 1 to 2. The log of 1 goes to 0, the log of 2 base 10 goes to about 0.3, and that's why you have about 30% of the numbers having a first digit of 1, because if the logarithms are equidistributed, there's going to be a little bit of a bias in the original number. This is another way of just looking at it, just putting it vertically rather than horizontally, and now to calculate the probability of a first digit of d, it would just be the log base 10 of d plus 1 minus the log base 10 of d. So this is the key equivalence. And it really shows the power of the right perspective. So I love Rubik's cubes. It turns out these two cubes are really essentially the same if you know to hold this cube at a 45-degree angle and view this whole thing, this blue-orange combination as one side, is that's what's going to turn nicely. So some examples of some Benford systems. So 2 to the n is Benford base 10 because the log of 2 base 10 is irrational. A little bit more interesting is that the Fibonacci numbers are Benford. And you can see this by taking the recurrence relation. You can solve and find Binet's formula. So I'm not going to go through all the details, but with a little bit of work or just divine inspiration, just check and see that this works. Here's a formula for the nth Fibonacci number. When n is very, very large, since 1 minus root 5 over 2 is less than 1 in absolute value, this tends to 0. So the nth Fibonacci number is essentially 1 over root 5 times an irrational number to the nth power. So when we take the logarithm, it's basically n log of the golden mean plus a shift. Most linear recurrence relations are Benford. I'm not going to go through the exceptions. Looking at the first 60 values of 2 to the n, I had just said to you it's Benford, but when you look at this, we only have one value of 9. we observe only 0.017, or your 1.7% rather than 4.6. Now, the ones and the twos look pretty good. Why is the data so bad? Well, the data is so bad because 2 to the 10 is 1,024 is almost 10 cubed. And so every time you increase by 10, you almost return to where you start. So it's going to take a long time before this sets in. This is extremely important because for a lot of applications, we're concerned with how many data points do we need before we can be reasonably confident that something fishy is happening. All right. Looking at some other numbers, looking at the Euler-Mascheroni constant gamma, E, and pi, looking at chi-squared tests, the smaller the value, the better the fit, we can see the first two are pretty small, but the second for pi is all over the place. And if you plot, I'm going to do a log of the chi-squared just to save a little bit of space because going all the way up from 46 down to 0.05 covers a lot of ground. And again, if you haven't seen statistical analysis like this, absolutely not a problem. We'll have a little lecture for those of you who are interested. You can see this beautiful, almost periodic pattern in the fluctuations of how close the fractional parts of pi mod 1 are for up to 100, 200, 300, 400, and so on. And if you look, it almost looks like it has a period of about 175. And it turns out pi to the 175 is 1.0028 approximately times 10 to the 87. So every 175 times, you almost return to where you started, padded by 87 zeros, but not quite. And it's that not quite that makes all the difference and has Benford set in. So a natural question to ask is, well, why are so many things Benford? So a great example is to look at streets. So not all data sets will satisfy Benford's law. So imagine you have a long street of length L. If you have L equals 199, you've just ended with 100 houses with 1 as their first digit. Whereas if you end with 999 as the last house, you've just had a huge stretch of non-ones. And so it turns out that the fraction of houses with the first digit of 1 will oscillate between 1/9 and 5/9, depending on how long your street is. And so this is just a plot of the percentage as a function of L. It's much better if we do a log plot and plot the probability of the first digit as a function of the log of the street length, and then you can really see what's going on in the periodicity. Well, what if we have many streets of different lengths and we amalgamate them? And so this goes back to the amalgamation idea we talked about earlier. Well, imagine we have 1,000 streets and each one has 10,000 houses. Then we get a nice uniform distribution for the first and the second digits, and it's very far from Benford. But now let's amalgamate a little bit. Let's introduce a bit more randomness. So imagine we have 1,000 streets, and each street has a length randomly chosen from 1 to 10,000. And when we amalgamate like this now, it's a little bit closer to Benford. And now what if we do random of 10,000? So we choose a random number from 1 to 10,000, and then we choose a random number from 1 to whatever we just chose, and we do that 1,000 times, and we see it's much closer to Benford. And if we do random, it's getting extremely close. And you can talk about rates of convergence. You can talk about what systems this would model. Little basic probability, and one of the reasons we love calculus so much is calculus gives us areas under curves, and areas under curves are often probabilities. So we say x is a random variable with density p of x. If the integral under the curve is 1, it's non-negative. The probability we take on a value between a and b is just the area under the curve from a to b. And so the mean value is going to just be x times p of x. This variance, or how spread out things are, is x minus mean squared times the density. And independence is knowledge of one random variable gives no information of another. So if you've seen a little probability, I can give you a quick explanation of why many systems are Benford. So the big result in probability is the central limit theorem. If you have a bunch of independent, identically distributed random variables, finite mean, finite variance, finite moments, then the sample mean converges to being normally distributed. And if I adjust things appropriately, I can have it converge to something with mean 0, variance 1, but I could also just look at the sum of x1 through xn. So let's look about sums of uniform random variables. So here, if I just take the uniform on -1/2, 1/2, I can adjust it to have mean 0, variance 1 a little bit. And I have, here's my uniform distribution with mean 0, variance 1 compared to a normal curve. And you can see it's okay, but it's not great. If, however, I now do sums of 2 uniform random variables, again, appropriately normalized, actually it's now pretty close to the Gaussian. And if I do sums of 4, not bad at all. Sums of 8, even better. As an aside, you can see why we care about the central limit theorem, because if I try to explicitly write down the density of the sum of 4, you can see, oh my God, it's split, it's fractured in so many different ways. And this is just the sum of 4 uniform random variables. Imagine how worse it is in general. But this gives you one of the ideas of the tool that we're going to use is to try to look at limiting behavior, where rather than writing down exactly what something is, we can write down something that's tractable that does a really good job of approximating. Why does this lead to benefit? Well, if your logarithm is normally distributed with growing variance, it turns out that a normal distribution with growing variance, mod 1, becomes uniformly distributed. So here, let's say the variance is 0.01. Well, what does that mean? Well, it's very unlikely to be more than 2 standard deviations away from the mean. So if I go from 0 to 0.2 or 0 to negative 0.2, and negative 0.2 is the same as 0.8, we can see it is pretty close. And again, this is the variance, so the standard deviation is the square root of that, which is why it's about 0.1. If I increase the variance to 0.1, you can see it's getting a lot closer to the uniform. It's not there yet, but it's closer. If I take the variance to be 0.5, you might say this doesn't look that uniform, but then you have to look at the axes. Always look at the axes, look at the labels. It's going from 0.99990 to 1.0001. And you can see that the fluctuations are minuscule, and it's essentially a uniform distribution. And so whenever you see a product, you should always take logarithms. So if I have a bunch of random variables x1 through xn, and I look at their product, a lot of processes are described like this. Maybe you have a random bar, you have a random length, width, height, density, and you want to evaluate the cost of it. Well, let's let y be the log of xi, and let's let vn be the log of the product. Well, the log of the product is the sum of the logs. By the central limit theorem, if everything is nice, this will become normally distributed with the growing variance, and we only care about things modulo 1, and so that is going to give us benefitness. And again, this is just one of many possibilities. So in terms of applications, I want to talk about one fun one was an audit of a bank revealed a huge spike of numbers starting with 4 8s and 4 9s, most due to one person. And when they zoomed in, they realized that what was going on is the bank had a write-off limit of 5,000. So operatives could write off anything under 5,000 without an internal investigation. And again, if you're the bank, it's not worth investigating a $13 missing credit card, but $20,000, yes. And so someone was having their friends sign up for credit cards, run up bills, and then throw them away. So this is just one of many possible applications. I want to share another one right now, which is related close to home. And this is from some analysis I did with some colleagues after the 2020 presidential election. So a lot of people were saying that there was fraud in the election, and a benefit analysis indicates suspicious things were going on. And so one of the examples that was frequently used is that the benefit vote totals in certain key places were very far from Benford's law. And so, for instance, over here is some data from Philadelphia precincts for Biden from 2020. And you can see that there is significant deviation from benefitness. But if you think about it, it's actually quite reasonable that there should be significant deviation. Imagine most precincts have a similar number of people, a similar percent vote, and there's a similar preference for candidates. Well, if that's the case, you should be seeing similar values as you go from precinct to precinct, and the distribution is going to be constrained by the size of all of these quantities. And so one of the ideas I had years ago was, instead of looking at things base 10, to look at things base 3. The advantage is, the number 81 is not even 2 full orders of magnitude base 10, but it's 4 orders of magnitude base 3, and it spreads things out. And if you look at the data base 3, you can see that the fit is almost perfect with Benford's law. So there's been a lot of use of benefitness to detect fraud. And one of the things I would love to investigate with students this summer is trying to refine these tests, try to get a better sense of what does it mean for a deviation to be significant? How many data points do you need to be confident? Can we do other tests? And so that is one possibility. Another project that I would like to look at is to look at benefitness in other settings. And so here is a video of the Mandelbrot set. If you don't know what the Mandelbrot set is, don't worry. And so what I'm doing is I'm zooming in. This is an example of a fractal. And fractals have a remarkable structure, a lot of great self-similarity. And you can see over here, you have lots of different regions coming in at different sizes. There's lots of different quantities you can associate to sets like this. And I would be very curious to look at the distribution of various quantities related to these sets and see, what can you say about the distribution of digits on these various scales? And so I will let this zoom in a little bit longer. If you have any questions, again, please let me know. I am happy to chat. I'll put it back to the very first slide. Have a great day.